All right, we are here to cover the material that was covered in class on Friday, January 22nd. And let me get this out of the way. There we go. So, what we're doing today is we're actually starting off with chapter 11, which is about alkynes. All right, and we've talked about alkynes before. Right, what is an alkyne? It's something that has at least one carbon-carbon triple bond. All right, we talked about these a good bit last semester when we talked about IR spectroscopy. All right, just like with alkenes, there's a couple of different types, right? Just depending on where the triple bond is located. You could have the triple bond at the end of a carbon chain. This is called a terminal alkyne. Or you could have it in the middle. That's called an internal alkyne. All right? And actually, being able to recognize the difference is probably a little bit more important here than it is in Chapter 10 with alkenes, because we're going to see that terminal and internal alkynes do some different things sometimes as far as their reaction chemistry. All right? So just sort of keep that in mind as we go forward. All right, so we're going to get into reactions of alkynes here in just a minute. First, I want to briefly touch on the nomenclature, right? Anytime we introduce a new family of compounds, we've got to learn how to name them. Fortunately, the nomenclature for alkynes is very, very simple. If you know the nomenclature for alkenes, you know the nomenclature for alkynes, pretty much. All right, so, that's a really weird looking N. Alright, so nomenclature. Basically what you do is you follow the same rules that you had with alkenes. Right? With alkenes, we found the longest carbon chain that contained the carbon-carbon double bond. With alkynes, you find the longest continuous carbon chain that has a carbon-carbon triple bond. Right? There's only one exception to this. Instead of using the suffix -e, you're going to use the suffix -e for alkyne. Okay? Alright, let's take a look. If you were to have something like this, right? Rule number one, find the longest continuous carbon chain that has your triple bond. All right, so that would be 1, 2, 3, 4, 5, 6, 7 carbons, I believe, right over here, right? So what's our parent chain going to be? It's going to be heptyne, because it's 7 carbons and it's got a carbon-carbon triple bond. All right, then you want to start numbering, right? With alkenes, we started numbering to give the carbons and the double bond the lowest possible numbers. With alkynes, we do it to give the carbons and the triple bond the lowest possible numbers. So, 1, 2, 3, 4, 5, 6, 7. All right, you have to describe where you introduce your triple bond, just like with alkenes. Our triple bond first appears at carbon number 2. So that would be 2-heptyne, and then you put in your substituents. Looks like we have methyls at 5 and 6, so this would be 5, 6, dimethyl 2-heptyne. Yeah, like I said, pretty much exactly the same as what you learned for alkenes, except substitute Y and E instead of E and E. All right, so I'm not going to get exhaustively into these since they're so similar to alkenes. But if you have any questions on them, let me know. One thing I do want to sort of highlight here couple of things, actually. The first thing is something like this. Oftentimes, I go through some examples of both cyclic and acyclic molecules to do nomenclature. So this would be, theoretically what a cyclic alkyne might look like. And, whoops, if we were to go ahead and name what this would theoretically be, as you might expect, it would be cyclopentine. All right. Now, that being said, for all intents and purposes, we're never really going to deal with cyclic alkynes. There's a reason for that. For all intents and purposes, they don't exist. They theoretically could exist, but they would be extremely difficult to make and to remain stable. So, we're just not going to see them. Here's a good question. Why are they so unstable? Why are they so unlikely to be made? Well, let's take a look at that. Goes back to all that chapter 1 stuff, right? Take a look at the carbons that are involved in your triple bond. What's the hybridization of each one of them? Hopefully you can recognize that they're both sp hybridized. If they're sp hybridized, what's their geometry? Should be linear. And what's the ideal bond angle for a linear geometry? That's 180 degrees. 180 degrees is basically just a flat line, right? And so as you can see here, the bond angles that you would observe in something like this, the cyclic system, they deviate so much from the ideal 180 degree bond angle, that just introduces way too much angle strain. We've talked about the fact that cyclic compounds can be tricky because of angle strain, deviation from the ideal bond angle. It's just too much in this case, right? It's too far away from that 180 ideal, so really they just don't happen. Also, kind of related to this, I want to highlight something that you're probably going to see in how alkynes are drawn. If I, whenever I write this, whenever I write this alkyne, right, 2-butane, technically the way I just drew it is incorrect. There's a more technically correct way to draw it, and it's like this. And you can probably guess why, right? It's because the drawing on the right more closely represents the ideal bond angles of 180 degrees that are present. All right, so it appears more of a straight line than, as a zigzag. There's no cis or trans or E or Z or anything like that with alkynes because the bonds don't actually stick out on either side of the triple bond. They're sort of parallel with it. However, one disadvantage of this is that oftentimes the carbons are really hard to see. We've always learned that every corner is a carbon, right? So, that one and that one. Sometimes people have real trouble distinguishing these. So, just for teaching purposes, I usually just go ahead and draw the zigzags anyway. But you'll probably see this representation occur quite a bit in textbooks or outside sources. So, just kind of be aware of that. All right. One last thing related to nomenclature and preliminary information. All the IUPAC that we talked, all the nomenclature we talked about previously was IUPAC, right? There is one particular alkyne that is very well known by a common name, and that's this guy. It's the simplest alkyne, C2H4. If you want to do the IUPAC name of this is called, ethyne. But you have probably heard it under another name, all right? If you happen to know anybody who is involved in welding, right, which I have no idea if you do know anybody who welds, but if you do, you probably know that they use something called an acetylene torch, right? That is the common name for ethyne, is acetylene. So that's what they're referring to. Right? Most other alkynes are, basically known by their IUPAC names, but that one's really, really well known. So I wanted to make sure that, we kind of highlighted that. All right. All right. So from there on in class, we shifted gears and we got into reaction chemistry, reactions of alkynes. All right, and you'll notice that, just like with alkenes, alkynes have pi bonds, right? Well, what did we do with pi bonds and alkenes? We did addition reactions. And that's what we're going to do here. We do addition reactions with alkynes. All right? We're going to go over 4 different addition reactions that alkynes are involved with. Some of them, certain ones of them, are going to be very, very familiar with what you learned from alkenes. There's going to be a couple that are going to deviate quite a bit. All right, so let's sort of dive in and take a look. First of all, let's look at hydrohalogenation. All right, so if you remember, when we did hydrohalogenation of alkenes, one of the carbons in a double bond got an H, one of the carbons in a double bond got a halogen, right? That's why I call it hydrohalogenation. Same basic thing happens here in alkynes as well, right? So we could have something like this. All right. Now, one major difference between alkenes and alkynes, of course, though, is that alkynes have 2 pi bonds. Alkenes only have 1. That makes a difference because since alkynes have 2 pi bonds, that means they can do hydrohalogenation twice. All right? So whenever we set this up for an alkyne, we almost always do 2 times, or 2 equivalents of reagent. All right? So let's see what's going to happen. All right. Well, the mechanism's going to proceed the same exact way that it did with alkenes. Right. You have a strong halogen acid. It can give up an H to one of the carbons here in your triple bond. All right. This is a symmetrical molecule, so it doesn't matter which one. I'll just put it on the left carbon, and that's going to leave a carbocation right there. Br minus can come in, and you can get this, right? Just exactly what we did with alkenes. The only difference is we have an extra pi bond left over at this stage. So, guess what? We have an extra pi bond, we have an extra equivalent of HBr, we can do it again, all right? We grab the H there, and that leaves a carbocation at that carbon. The other Br minus can come in. And voila, we get this product. All right, so you see, within the triple bond, one of the carbons gets 2 H's, one of the carbons gets 2 halides. All right, this is called, well, a dihalide because it's got 2 halogens. It's a very specific type of dihalide, though, because it's got the halogens on the same carbon. When they're on the same carbon, it's called a geminal dihalide, sometimes shortened to gem. All right? So whenever you do hydrohalogenation of an alkyne, you're always going to get a geminal dihalide because you get 2 consecutive hydrohalogenation reactions. One other kind of nice thing about this that is not observed with alkenes is that due to the very nature of the reaction, it's impossible to make new stereogenic centers. So we don't have to worry about stereoisomers. Yay for simplicity, right? Yeah. One of the carbons is going to get 2 hydrogens, which are exactly the same. One of them is going to get 2 identical halogens, so Yeah, neither one of those can ever be stereogenic. All right? This is at the point where I would usually ask if there's questions, but hey, this is a video, so I can't do that. Of course, as always, if you have any questions about any of this, just shoot me a message and we can talk about it. All right? Now we could take this one. Let's just use HCl this time. All right. So on this one, there's basically... Oh, hold on, I forgot 2 times. Basically, it's the same thing, except there's one extra decision you have to make, right? Not a symmetrical molecule, so you have to make a decision as to which one of those carbons in the triple bond is going to get your H. All right? Well, we notice, of course, that one of them has a higher substitution pattern than the other one, right? So we're going to follow Markovnikov's rule. Markovnikov's rule, as part of Markovnikov's rule, we state that, whichever one of these carbons is less substituted gets the hydrogen, right? So the hydrogen, has to go on this end carbon and not on the middle one, right? So Markovnikov's rule applies not only to alkenes, but also to alkynes as well. From there on out, everything proceeds exactly the same as the last example. We finish off our first hydrohalogenation like that. And then we do it again. Boom. Geminal dihalide. But a specific one. Cls are both on the second carbon from the right, not the furthest right one. Okay? I'll show you one more, just to show you that it can get a little bit more complex than this. You don't always have just a singular product. Okay? You could have one like this. All right, this is an internal alkyne, right? It's not symmetrical, so these 2 carbons are not exactly the same. However, they do have the same level of substitution, right? Each of them has one R group hanging off and no hydrogens. So you can't really use Markovnikov's rule to figure out that one of them is going to be more likely to get the H than other ones. In fact, the H is just as likely to go to this carbon as it is this carbon. So guess what? It does both. Yeah. So this is going to be one of those cases where you could end up with 2 H's on the middle carbon, 2 Brs on the left-hand carbon, or vice versa, right? Because there's no favorability for either one of them in particular. I'm not going to go through the mechanism here. I think you can probably do that on your own by now. But here would be the 2 products that you would get out of this reaction. And I think if you follow the mechanism, it will lead you to these 2 products. Again, if not, please let me know and we can work through it. Okay? All right. All right. Let's look at the second major addition reaction, and that's going to be halogenation. And again, this is something that we did last chapter, right? All right, so we could have something like this. Last chapter we learned that, if you do a halogenation, your alkene would react with either Br2 or Cl2. Same thing here. Br2 or Cl2. Again, the difference is we're going to use two equivalents instead of just one. And the mechanism is exactly like we learned last chapter, right? So just to refresh you, well, that's an ugly pair of electrons. Oh dear. So ugly, but you get the point. All right, so this Br2 is going to polarize. Right? One of the Brs becomes a negative ion. The other one forms, remember our little triangle? Yeah, it forms the bridged polonium, just like I did with alkenes. The only difference is our bridged polonium has one extra pi bond that's left over. Then your other Br comes in, breaks open the ring, and you get this. And that's the end of stage one of the reaction. But hey, guess what? You got another Br2. And you got another pi bond, so this can happen all over again. So you see there's a lot of Brs floating around here. Alright, so you form another bridged polonium. And that last Br minus comes in, adds and breaks the ring, and voila. You get this. Alright. That is called a tetrahalide. I'm going to just write it down here because I'm running out of room. Tetrahalide because it's got 4 halogens on it. One of the carbons in the triple bond gets 2. The other one also gets 2. So this is a tetrabromide to be specific. All right. Again, just like with we saw in the last example, there's no way to make new stereogenic centers here, right? Because each one of the carbons is always getting 2 of the same things, in this case halogens. All right? Very, very predictable reaction. You don't even have to worry about Markovnikov's rule here. It doesn't apply. So if you see a triple bond and you're doing a halogenation, you know each one of the carbons involved gets 2 of that halogen. This is probably one of the simplest reactions to be able to predict the answer of. Okay? All right. So I mentioned a couple of these, would be simple. Those were the simple ones. All right? And a couple of them are also going to be a bit more complex. All right? So we started to get into one of those in the class. So I'll go ahead and catch you up to the point we are in class. We started talking about hydration. All right? Now, we did hydration of alkenes, right? We learned that if you take an alkene and then add H2O and H2SO4, you can get an alcohol, right? One of the carbons in a double bond gets an H, one gets an OH. That's why we call it hydration, because collectively it's water, and you always make an alcohol. We can see one difference right off the bat, and I'm just going to write general terms here instead of structures. I mentioned terminal alkynes and internal alkynes are sort of different sometimes. And that starts to come into play with hydration. First of all, the reagents that are needed for hydration. For an internal alkyne, it's exactly the same as with alkenes. You just need water and sulfuric acid. Okay? Now, with terminal alkynes, it's a little bit different. You still need water, you still need sulfuric acid, but you also need an additional catalytic agent, an additional catalyst. And it's a mercury-based compound. Hg, come on, there we go. HgSO4, mercury sulfate. All right. So if you're doing a terminal alkyne hydration, you got to have all three of these, or the reaction won't work. It can be a little confusing because if you go through the mechanism of this, mercury sulfate actually does not appear in the mechanism. It doesn't really do anything as far as causing new bonds to form or old ones to break or anything. It's just basically sort of there to help stabilize a particular transition state. So you don't see it in the mechanism. You just have to remember it's got to be there. Okay? All right. So that's one place where it's a little bit different. Let's get into the mechanism. And I think from memory yesterday in class, we only did an example with internal alkynes before we ran out of time. So that's where I'll catch up here. And then we'll do terminal alkynes in class on Monday, and you can be there for the Zoom. All right. So let's say we had something like this. Okay, so let's walk through the mechanism. It starts off exactly the same as you would have expected based off of what you learned about alkenes, right? Just like before, you have extra electron density. You have a strong acid that wants to give up a proton. So it'll add to one of those carbons. Perfectly symmetrical molecule, so in this case, again, it doesn't matter which one we add to. You can probably hear my dogs barking every so often. Sorry about that. All right. Okay, so that gives us a carbocation, and just like we saw last time, a water can come in, nucleophilically attack. It's going to give you this. All right. HSO4 minus. Come in, grab one of the H's, and that gives you this. Okay. Here's where things get a little bit different. First of all, I want to highlight this structure here. Here you see a carbon-carbon double bond, and one of the carbons of the double bond also has an OH. All right? This has a special name. This is called an enol. All right? Now, one thing about enols is that they're not very stable. And in fact, what happens with enols is something that's kind of unique, something you haven't seen before. What enols do is they actually sort of enter into an equilibrium with an alternate form that's a little bit more stable. All right. I'm going to come back to the full reaction mechanism. Because I'm running out of room, I'm going to erase this part here so I can sort of do a little side discussion up here. All right, so I'm going to redraw this. All right, so yeah, enols are not very stable. And like I said, they tend to enter into an equilibrium with sort of a, for lack of a better description, rearranged version of it. This one has an enol form, and it reaches an equilibrium with what we call the keto form, which is the more stable form. And this process of interconversion is called tautomerization. And the enol and keto forms are referred to as being tautomers of each other. Okay? Now, you might like a definition of what a tautomer is, right? Tautomers has a very specific definition. Tautomers differ in the placement of one pi bond and one hydrogen. It is an oddly specific definition, but it's accurate. If you look at these two forms here, right, in the first structure on the left, we have one pi bond but it's located between these two carbons. Here we also have one pi bond, but instead of a CC double bond, you have a CO double bond. All right. In this structure, you have an H here on the oxygen, and you only have one H on this carbon. Over here, this oxygen doesn't have any H's, and this one has two. So it's, effectively like you just sort of picked up that H off the oxygen and put it on to this carbon. Okay? So that's what tautomerization is. Those are the two types of tautomers that we can see here, enol and keto forms. There's actually several other examples of tautomerization in organic chemistry. This is just the first type that you guys have seen. All right? And one thing that's kind of interesting and somewhat, maddening sometimes is the fact that there is no one universal mechanism for how tautomerization occurs. It just occurs based off of whatever's in the system, right? It finds a way. So if you're a Jurassic Park fan, you remember that when Dr. Ian Malcolm said nature finds a way? Kind of applies here too. If you haven't seen Jurassic Park, you need to watch it because it's a really good movie. All right. Here, I can tell you how the mechanism of tautomerization occurs. All right, so I'm going to go back to the mechanism of that example I was doing just a minute ago. All right, so you have some H2SO4 still over here, right? And just like we saw before, it's going to add to the double bond according to Markovnikov's rule. And it's going to make a carbocation right there. Okay? Now, however, what's going to happen is you're actually going to form a resonance structure because a pair of electrons can swoop down from the oxygen to make a double bond. Whoops. Didn't mean to do that. Whoops. Okay, come on. My program's doing weird things here. All right. And when it does that, it's going to give the carbon a positive charge. And then lastly, your HSO4 minus grabs this H, and that gives you your final product. Trying to circle it. There we go. Kind of ugly looking, but it's the keto form. Technically speaking, you do have a little bit of the enol left in there since it's an equilibrium, but for all intents and purposes, it's going to be just the keto form. Okay? Here's a rule, hard and fast rule that you can remember. I guess I should write this down for you. If you take an internal alkyne and you do a hydration, your product will always be a ketone. And that's what this is up here. This is a ketone. Don't get keto and ketone confused. They don't mean the same thing. Keto is just the tautomer of an enol. Those don't always turn out to be ketones, though. This is a ketone. Just like we learned, go back and review your IR spectroscopy notes so you can see what the general structure of a ketone is. Okay? So if you do an internal alkyne hydration, you always get a ketone. However, you don't necessarily always just get one ketone. You could have something like this. And again, I'm not going to go through the whole mechanism of this one. You are more than welcome to, and you should be able to at this point. Let's say you had something like this. All right, I'm going to tell you just straight up, you can get two products here, and you will get two products. All right, it's all based off of the fact that in the very first step, you have two carbons here that are different, because it's not symmetrical, but they have the same substitution pattern. So that means either one of these could grab your H. And that means you could form two different carbocations. That leads down the line to two different ketones. So either one of those carbons in the double bond, in the triple bond, could end up with your carbonyl group, because this initial proton in the first step could go to either one of them. So, yeah, sometimes you will end up with a mixture of products whenever you do this reaction. Other times you won't. Just pay very close attention to that first step of the mechanism. See how many different carbocations you can make. Okay? Cool. Hey, guess what? You are all caught up now. So this is where we stopped in class on Friday. We will pick up on Monday talking about, we're going to do the same reaction but with terminal alkynes, and then we'll get to the fourth addition reaction. All right? So, and you've got the Zoom link. So if you have any questions at any point for any of this, just let me know. All right? I'll talk to you later. Bye-bye.